Hi, in this video, we want to take a look at the Poisson distribution. Okay, so in this distribution, we're interested in counting the number of events over a time period. Okay, so this could be like number of times somebody was arrested in a given year. This could be the number of accidents at an intersection during a week. This could be the number of people that pass through a door during an hour. Something like this. Okay, so the Poisson distribution, something that's very important about it is that we start at 0, then we see 1, then 2, then 3, then 4, and so on, because we're counting. Now, something that's different about the binomial distribution, think about like flipping 5 coins at the same time. If I flip 5 coins at the same time, the outcome is like automatic, like they all happen at the same time, potentially at the same time. Also, there's a cap on what could happen. Also, think about rolling dice, or maybe just one. If I'm rolling a die, I have 1, 2, 3, 4, 5, or 6. Those numbers, if it's a 5, to get to 5, it just happens. I don't go 1, then 2, then 3, then 4, then 5. Poisson distribution, if you're counting with a number and you start at 0 and it builds up, then you're probably choosing the right distribution when you use Poisson. Okay, so something about this is if I'm counting over a time period and I want to use, like, there could be multiple time periods going on for the Poisson distribution, I really want the intervals to be independent and identically distributed for their counts. As long as I have that, I have a lot more flexibility and a lot more power in how I can model things. Even if as long as they're independent, they don't even have to be identically distributed. We can still do things, but it's a little bit more mathematically more complicated, and we're not going to talk about it here. So the Poisson distribution is the key aspect to it is the probability of getting a particular value, particular count, is going to be lambda to the x divided by x factorial, and then I multiply the exponential e, the exponential base, to the power of negative lambda. All right, so lambda is the average number of occurrences during the time period. Okay, now something that's important about this is about collecting data. For one observation, when I count, I could do like 1 minute, then the next one has to be also over 1 minute, and the next one has to be over 1 minute. I have to have like 1 minute, 1 minute, 1 minute for my time intervals. I can't do a minute, then 5 and 6 and a week, anything like that. I have to have a constant length of time if I want to be able to compare my results. Now, the expected value is lambda. It's the average number of occurrences during the length of time, and the variance, just by happenstance, ends up being equal to the expected value. So something that we can do when we check our data, if I have count data and I'm unsure, is it reasonable to model this as a Poisson distribution? If the expected value and the variance are around each other, then it's probably a good idea. Now, something that we can do is I can change my interval of time. Let's say that I have lambda for over 1 minute. Now I need to do things now over 10 minutes. Well, what I can do, if I proportionately increase my time, I can, by the same proportion, increase my lambda and have a new Poisson random variable that gives me information, as long as I have that independent and identically distributed aspect. So here, let's say that instead of dealing with 1 minute, I had to deal with 10 minutes of counting the number of occurrences. Well, then I would just take lambda times 10. Okay, well, what if I have, let's say, the number of arrests per year, and then we need to change this up. I need to model the number of arrests per month. Well, what I could do, I could have t equal to 1 over 12, and then I divide the average by 12 for the modeling, and that will work out. Now there, technically a year does not perfectly divide by 12 to give us months, but it's pretty close. All right, so the first thing we should ask ourselves is, does this define a probability? Well, first and foremost, everything in this formula is going to be positive. There's no zeros, there's no negatives, so that's okay. Next question is, do these all add up to 1? Well, if we think about it for a moment, and we remember from calculus, the e to the lambda, its Maclaurin series is the sum of lambda to the x divided by x factorial. X goes from 0 to infinity. So if I go through and I divide both sides by e to the lambda, then I see that 1 is equal to what I get when I add all these up. All right. So then, that's nice. That's good. All right. So now what about the expected value? All right. To compute the expected value, I'm going to use a similar trick to what I've done before in another video, where I take to compute the expected value here. Of course, by the definition, it's going to be the sum of x times its probability. All right, so when I look at this, I see that that's kind of an awkward situation. So let's try to rearrange some things. Let's go ahead and let's factor out everything that doesn't have an x, because here I have infinitely many like x terms going on, and I notice that e to the negative lambda isn't really doing anything in here, so I'll factor that out. And I realize I have x and lambda to the x. That's almost a derivative, almost, not quite. So I'm going to go ahead and factor out a lambda here. And that gives me x times lambda to the x minus 1. All right, so now that is a derivative with respect to lambda. So boom, I have this. Okay, so now I look at this whole part here, and I realize I have infinitely many terms, and I have a limit as things get infinitely small. Remember, limits, derivatives are limits, and I have an infinite summation, so I can't switch the order of limits freely, but here I can, by happenstance, because there's some theoretical math going on that we're not going to talk about any deeper, that in this special situation, I'm allowed to switch the order of the limits. Okay, so when I do that, this whole thing becomes the sum of lambda to the x divided by x factorial. Then I have a derivative on the outside. Okay, well this, from the formula we looked at a moment ago, this is e to the lambda. So this summation right here becomes e to the lambda. Now I see that I've got a derivative of e to the lambda. That's the easiest derivative from calculus because nothing happens. So this derivative is e to the lambda. And then I multiply by e to the negative lambda. And so it cancels out, so I get the expected value is lambda, just like we said above. Okay. Now, what about the variance? The variance is going to be the same trick, but I'm going to use a second derivative this time. Okay, so remember, when I'm dealing with variances, there are two major formulas to work with. I can go the expected value of x squared minus the expected value of x squared, or I can use this formula here, or I take the expected value of x times x minus 1 plus the expected value of x minus the expected value of x squared. Okay, so for this problem, this is the better presentation. And the reason why this one is good is because if I can set something up like a derivative, a second derivative in particular, this sets me up to be able to accomplish things. And that's exactly what I'm about to do. So let's go ahead and compute the expected value of x times x minus 1. All right, well, by the definition of expected value, it's just a sum of x times x minus 1 times the probability. All right, and I add them all up. All right, so now I look at this and I see this is very similar to what I had before. I go ahead, I factor out e to the negative lambda, put it here. I have lambda squared that I go ahead and factor out. And this part here, that looks a lot like a second derivative with respect to lambda. It's important, it's with respect to lambda. And so this part becomes the derivative of lambda to the x with respect to lambda. Okay, and now using some theory from calculus, I know I can switch the order of that infinite sum and the derivative. Okay, and so then I get this part. But then I realize, hey, I've seen this already. That's e to the lambda. So boom, that gets replaced with e to the lambda. Take the derivative, it's the easiest. Oh, this should be a second derivative. Oh, that is a mistake. This should be a d to the power 2, lambda to the power 2, d to the power 2, lambda to the power 2, d to the power 2, lambda to the power 2. And then boom, everything works out after I take care of that typo. All right, so now I know what this expected value is. I know what this is because that was the expected value we computed. And then I take that same value and square it. And boom, we have our variance down here. Just plug and chug. I see I have a lambda squared minus lambda squared. Those cancel. And boom, we get our result. Very, very nice. Okay, so now there is a solid connection between the binomial distribution and the Poisson distribution. Okay, so let's think about the situation where we want to count the number of occurrences of an incident over a time span. Now, what I'm going to do, I'm going to take that time span, I'm going to chop that time span up into smaller sub-intervals where realistically I could only have one incident at most in each sub-interval. Okay, so if I do that, well, I have n sub-intervals, and well, I'm going to go ahead and let's say that lambda is the true average of what would happen over the entire interval. Well, number of sub-intervals times the probability of an incident in its sub-interval when I can only have one incident per sub-interval tells me that n times p has to be equal to lambda if I'm using incident or no incident inside sub-interval to define a Bernoulli random variable. Okay, well, by this construction, I can see that we have a binomial distribution for the number of incidents over the entire interval. Okay, well now, so right here, I've got a probability for figuring out, how many incidents I'll have. What if I make the sub-intervals smaller? What if I chop them up really tiny, and and then chop them up again and and they're all equal width and get really small sub-intervals? Well, that would be taking a limit as the width goes to 0 or the number of intervals goes to infinity. So what I'm going to do, I'm going to take this probability to kind of see what happens. I'm going to take the limit as n goes to infinity. All right, well, I just basically slap limit in front of both things. Now, on this step down here, I'm just rearranging terms so that I'm able to take the limit in a moment. So I take this n choose x, which I know involves a bunch of factorials. Here, I've simplified the top and got rid of the n minus x factorial on the bottom. Here is the other term in the bottom of that factorial. This part here is going to give me lambda to the x and n to the x, lambda to the x, n to the x. And then this part, I'm going to break up the part with the n over here. I'm going to break up the part with the negative x over here. I'm trying to break everything up. And the reason for this is so that I can take a limit in a moment. Now, when I do this, I can go through and I can take this fraction and I'm going to break this up into the product of similar fractions. All right, so right now it's one big fraction. I'm going to make it multiplication from a bunch of smaller ones, x of them in fact. And so here are all of those fractions mixed up. All right, and I factor out the lambda to the x factorial over here. And then I've got this term stays the same, and I move this one over. Now, when I'm taking limits, if all the limits are well defined, the limit of a product is the product of limits. Okay, so then what I'm going to do, I'm going to take the limit of each of these individual terms, because I can, because that's an easy way to go. And I notice that a bunch of things happened. So this part stays the same as lambda to the x factorial. This is a well-known limit from calculus of e to the negative lambda. Boom, we've got that. Now the rest of these, if I look at it, as n goes to infinity, this will all of these give me 1, because the fraction on the inside of the parenthesis becomes 0 in the limit. And then boom, we've got our probability. Now, something that comes out from this is that if I have large n and small p, I can approximate a binomial distribution using a Poisson distribution where lambda is equal to n times p. Also, when p is small, 1 minus p is approximately 1, which means that the variance from the binomial distribution is approximately lambda, and that's exactly what we would want it to be if we're going to be doing, we're going to be using Poisson distribution to approximate a binomial. Now, for the Poisson distribution in R, we have, of course, the distribution, we have the probabilities, we have the quantiles, and we have random number generator, the basic 4 that always come out of R. So X is the vector of non-negative integer values. So these have to be integers. Q are quantiles. P is a vector of probabilities. N is the number of terms to generate. And lambda is the expected value of the random variable. And R has the ability to handle multiple lambdas at the same time in a vector. So if I want the density, I go deep Poisson, and here I can go 0 to 10, 11 different terms. I've got lambda equal to 5 in this example. Here I can get the cumulative probability function. We can get our quantiles. Now notice something about this is that with the Poisson distribution, but we're saying potentially, even though it's a super small probability, there is no bound on how big the counts can be. And we can also do random number generation with our Poisson. All right, well, that's all I've got for you. Take care and goodbye.